Hi there. Thanks for joining us on Space Nuts, where we talk astronomy and space science twice a week, in fact. And I'm glad you could join us yet again. Today's episode has some great news, but also a bit of a sad reflection. It's 40 years since the Challenger Space Shuttle disaster. Can you believe that? 40 years. Of course, some of you listening to us won't remember it because you're 40. But for those of us who are a few years older, it is a very, very strong memory. We'll talk about that. On a happier note, we will reveal the Australian of the Year. I think most Australians will know who that is. How do you define a moon? That question has come up because of a potential discovery. And they think they know why black holes are getting big fast. We'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us as always is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello. It's good to be good.
It is good to be good. It's good to see you. It's good to be in a cool room because it's not cool in our part of the world at the moment. We're right in the middle of a week-long run of 40-plus Celsius temperatures. We've broken our record in Dubbo for the hottest day in January, and that was 46.1, I think we had, on Monday, on Australia Day, which, it was dreadful. I mean, it was just horrific. It's been a pretty rough week. My plants are suffering. There's nothing I can do about it. And I think we're going to lose a few. So unfortunately, that's the way it goes. I suppose that's what happens when they plant plants in an environment like this that don't come from here. They struggle. But yes, all is well with you?
Our plants pretty well are all natives in Marnie's garden. So they don't seem to mind, but we've got much more modest temperatures than you have here on the coast.
Probably about 10 degrees cooler, I imagine.
It's not quite that, but not far off. Actually, no, it's more like 20 at the moment. 20 degrees. Yeah, we're down at, but it's forecast to be 29 today. So
we're going to get to 41, I think, today. So I think we're already pushing towards 30 as I speak, and it's only, 9:30 in the morning local time. So we've got a lot to talk about, so we better get stuck into it. The first thing is something that I don't think anyone who was around at the time will ever forget. I'm talking about the Challenger Space Shuttle launch in 1986, and this is basically what happened.
T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1. And liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Control program. Roger, roll, Challenger. Good roll program confirmed. Challenger now heading down range. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles. Engines throttling up, 3 engines now at 104%.
Challenger, go at throttle up.
Challenger, go at throttle up. 1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles. looking very carefully at the situation. Obviously a major malfunction. We have no downlink. We have a report from the flight dynamics officer that the vehicle has exploded. Flight director confirms that. We are looking at checking with the recovery forces to see what can be done at this point.
And there it is. That was the launch of Challenger in 1986 in real time. And we heard the final words of the commander, Dick Scobie, when he said, "Roger, going with throttle up." And that was basically where it all went horribly wrong, Fred. The cause of the accident was ultimately blamed on the O-rings. The O-rings joined each section of the solid rocket boosters, and there were several of them, but one of them had a catastrophic failure, and the vehicle exploded as a consequence of that failure. And we all saw it. We all watched it. It was horrifying.
Indeed, it was. I remember it very well too, of course. So yeah, it was nothing to do with the throttling up. That was just
to get it going. Yeah, that's that.
And they throttle back for the maximum dynamic pressure region, where when you've got the biggest aerodynamic forces, you throttle back for that, and then throttle up again. And so it was eventually determined that what had happened was that the temperature on one side of the shuttle, it was a cold morning. It was a winter morning, 28th of January. 2 degrees, I think. It was 2 degrees above zero ambient when they launched. But one side of the the shuttle and its boosters were still at -2. And at those temperatures, those O-rings become effectively non-pliable. They don't, they're not flexible. And so that's what allowed the fact that it was not behaving properly, allowed gas to escape from that joint. As exactly as you've said, there are 4 sections to the shuttle booster, each sealed by O-rings, and it was the lower one where combustion was at its extreme. It meant the gases came through, and in fact, there is footage that shows exactly that, with these hot gases playing on the main fuel tank, the external fuel tank of the shuttle. So it was very much, their fate was sealed even before launch, basically. And there were people at the company who built the boosters, Morton Firecall, who knew that, and they were overridden in their warnings that this was likely to be dangerous. They
raised concerns a long time before this happened. In fact, they'd discovered damage in the O-rings from previous missions, and even the night before the launch, they held a meeting to say, "We don't think you've got to scrub the launch. It's not." It's not safe. Something dreadful could happen. And I think the factor that made the difference, as you said, was the temperature that morning, because previous flights were warmer. It was warmer.
Yeah. I think 12 degrees was the lowest they'd ever launched at, and it was 2 that morning, as you said. And one of the reasons for the reluctance to scrub the mission may have been the fact that we did have this teacher on board. Christina McAuliffe, that's her name, I think. She was a school teacher, not an astronaut. She'd engaged many schools across the country. So huge numbers of people were watching. And NASA had done that purposely, I think, to sort of inject some more interest into the shuttle program, because they'd had 25 successful launches and it was becoming basically routine. Very people were blasé about it. But just to also confirm that there were a further 87 successful shuttle launches after that. So the problems were fixed and the lessons were learned. It was a tragedy, of course, a human tragedy with the loss of life. I noticed something yesterday that blew me away, Andrew. there are 17 astronauts were lost in NASA programs. The three Apollo 1 astronauts who died in the fire on the ground of the Apollo 1 capsule. That was on the 27th of January, 1967.
Yes.
The Columbia disaster, when re-entry was basically turned into a disintegration because of damage to the shuttle wing. That was on,
wasn't it?
That's correct. That was on the 1st of February 2003. So these losses of life were all within a week of each other in anniversary times. It's quite amazing. So yes, the Challenger disaster, 59 years before, the day before, we'd lost the Apollo 1 crew, and it's a coincidence, but it's a spooky one.
It is very spooky. I remember where I was when the news broke. I just got in my car, and I naturally had the radio on, being someone who worked in the industry, and the news came on as I was backing the car out, and I just stopped in my tracks, and I just shook. I couldn't believe it. And what really haunts me is that only a week before, I'd been talking to my future sister-in-law, who was still in high school at the time, and she brought it up with me about the Space Shuttle program, and I said, what worries me is something horribly wrong is going to happen. Yeah. I think they're actually being too gung-ho. That's what I said to her. And I couldn't believe about a week later, this happened.
Well, you were right. In a way, that's sort of what led to it.
Yeah. But the same thing, as you mentioned, with the loss of interest in the Space Shuttle program from the public perspective, the same thing happened with Apollo. Like they were supposed to have more missions, but they just went, no one's interested anymore. So they stopped at 17.
That's quite right.
And I suppose these days, space travel has just become routine. There are missions going up and down all the time we never hear about because it's so very regular now. And when you bring in the private sector on top of that, there's launches every other day. It's just happening, and it was always going to go that way, I suppose. But you've got to spare a thought for the pioneers that sacrificed their lives to make all this possible, because without them, it just would never have got to the point it is now. And I think we've said it before, you go back to the history of flight, and we got to the moon in less than 100 years of the first flight by a human being in a purpose-built aircraft. It's just extraordinary to think that we could have leapt so far, so fast. And I suppose when you do that, there is a price. And this was one of the costs of space travel and aeronautics. And yeah, it was a very sad day, and one I will never forget, Fred. We will leave Challenger there to some happier news. And of course, the other day we celebrated Australia Day in this country, 26th of January. And every year we have the announcement of the Australian of the Year. Now, quite often it's a sports star. That usually happens, although in recent years they've been focusing more on the academic side of things or the medical side of things, which is good. This year, though, you must be really pleased. It is an Australian astronaut.
Absolutely delighted. Yeah, really thrilled about that. She's an astronaut who has been qualified under ESA's astronaut program, the European Space Agency. She hasn't flown yet. There's every chance that she will fly to the space station and fulfill a mission. Catherine Bennell Pegg is her name. I discovered yesterday, I was looking at dates yesterday, obviously, she is one day short of 40 years younger than me. But her birthday is the day after mine, so that's a non-coincidence. But not only an astronaut, but she is also director of space technology at the Australian Space Agency, which was very much close to my heart in the work that I did for the government. The Australian Space Agency, a sister organisation within the Department of Industry, Science and Resources, where I worked. So a lot of friends there, and Catherine is absolutely well-deserved recipient of the annual Australian of the Year award, and she'll do great things with it. She wants to be very much a STEM ambassador as well for for education, for science, technology education. She'll do a great job. She's a lovely person.
Yes, she comes across that way, and I think the interest in space science is starting to really grow from strength to strength, and she will do a wonderful job in that regard, and maybe inspire other Australians to follow in her footsteps. And now that we have our own space agency, we certainly want that, don't we?
Very much so, yes. The Australian Space Agency was formed in 2018. It's still going strong. A lot of its functions are regulatory. It's all about regulating launches and things of that sort, but also promoting startups and things of that sort to encourage the space industry here in Australia, which was why it was set up in the first place.
Yeah,
Catherine's a great, a great cheerleader for that. It's brilliant.
Yep, she's got a busy year ahead of her now, because her Australian of the Year duties will be on top of what she has to do for her regular gig. So she'll be doing a lot more travel, a lot more speaking, a lot more engagements. It's a big job when you're named Australian of the Year. So I'm told.
Well, you never know, Andrew. One day.
Look, I'd be lucky to be named, my street member of the year. Not a big street either. But no, good luck to her, and congratulations to Catherine Bennell Pegg. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, Houston, we've had a problem here. This is Houston. Say again, please. Houston, we've had a problem. We've had a main beam undervolt. Roger, main beam undervolt. Okay, stand by, 13. We're looking at it.
Space Nuts.
Do you like that, Fred? We got some new links. I had a bit of time up my sleeve, so I created some new stuff.
It's a very appropriate one as well.
Yes, I thought so too.
Yeah.
Now, our next story is about defining what is a moon. This has come about after a study had been published, which is a peer-reviewed paper in the archive. It's looking at a really big gas giant, but they think it's got a moon that could force us to redefine what a moon is. Is that the way it goes?
Well, yeah, because it's big. That's right.
I got that impression.
Yeah. So this is work that's been done, actually led from the University of Cambridge, using a thing called an interferometer, which is one of these things that brings light waves together and watches them cancel out. And by doing that carefully enough, you can learn a lot more than you otherwise could. And there is an interferometer which is called gravity. Good name for it, because that's one of its tasks, was to kind of look at the gravitational forces around black holes, which is done very successfully around the black hole at the center of our galaxy. It's on the Very Large Telescope in Chile, and it's a way of you will know, and some of your listeners, some of our listeners will remember that the Very Large Telescope is actually 4 8.2 meter telescopes, which can be used together. Along with some auxiliary telescopes as well, and that's they're used together in the science of interferometry, which lets you look at objects in space in very great detail. And in particular, the scientists have been watching the orbit of a gas giant, exoplanet, which has the lovely name of HD 206893b. It's 133 light years from our solar system as the crow flies. But what they've done is they've watched the motion of this gas giant as it orbits around its parent star, which is HD 206893 itself, the B refers, at the end of that, refers to the gas giant planet itself. But what they've seen is that the orbit of this giant planet is wobbling slightly as it goes around. Little, deviations from a perfect ellipse, which are interpreted as being due to a moon. And by knowing the mass of or estimating the mass of the planet itself, you can estimate the mass of this moon, and it's enormous. It's many times the mass, if I remember rightly, something like 9 times the mass of Neptune, 40% of the mass of Jupiter, and when you compare that with the moons in our solar system, it's much, much heavier than anything, or much, much more massive than anything we've got. So that leads to the question, well, if you've got something that's 9 times the mass of Neptune, could you ever call it a moon? But the normal definition of a moon, or technically a satellite, is something that is in orbit around an object that is in orbit around a star, in other words, a planet. So do we want to bend that definition, or are we just content for this thing to be the most massive moon known?
Well, where do you draw the line? If the definition is a satellite orbiting an object orbiting a star, then that's it. Shouldn't matter how big it is, should it?
No, that's right. That would be my view. That you keep the basically keep the definition as it stands. What you do is you just extend your range of expectancy in terms of the size of these objects. In fact, there's a lovely comment. There's several comments from the lead author. I'm looking, just to say where we're looking at Daily Galaxy for this report, but it's a paper that's been published, I think, in Monthly Notices, again, one of the leading journals anyway. And the quotation from Quentin Kral, who's one of the authors, I think the lead author of this paper, some nice quotes. What we found is that HD 206893b doesn't just follow a smooth orbit around its star. On top of that motion, it shows a small but measurable back and forth wobble. The wobble has a period of 9 months and a size comparable to the Earth-Moon distance. This kind of signal is exactly what you'd expect if the object were being tugged by an unseen companion, such as a large moon, making this system a particularly intriguing candidate for hosting an exomoon. And goes on to say, this raises the question, because of the mass of this moon, this naturally raises the question of whether such an object should even be called a moon. At these masses, the distinction between a massive moon and a very low mass companion becomes blurred. However, there is currently no definition of an exomoon, and in practice, astronomers generally refer to any object orbiting a planet or substellar companion as a moon. So that's the bottom line. Yeah. There are not many known, and that's because moons naturally are generally small, and so their effect on the planet around which they're orbiting is too small to discover, whereas this thing is so big that its signal is really quite impressive. It's sufficient for this team to give us the paper that we're talking about. And just one final quote from Kral: "It's important to keep in mind that we're likely only seeing the tip of the iceberg. Just as the first exoplanets discovered were the most massive ones orbiting very close to their stars, simply because they were the easiest to detect, the first exomoons we identify are expected to be the most massive and extreme examples." It's a really good point.
And there it is. And yet again, we find in a potential new discovery that it's not what we would expect to be the norm. This is another thing that we may not have anticipated.
That's right. So yes. So I mean, the point is well made. Quentin's point is well made that the you're going to find the real outliers first, because they're the easiest ones to find. But at the same time, what you've said is true. The outliers are sometimes so surprising that they're difficult to believe. But we've got an outlier here that might well be the first of a new breed of or a whole new regime of exomoon discoveries.
Yeah. I didn't even think about exomoons. Like, we've discovered so many exoplanets now, and we continue to do so, but we haven't actually laid our eyes on an exomoon yet.
No, and in fact, we've not laid our eyes on most of the exoplanets. We've inferred their presence by indirect means. There are one or two that we can observe directly. But when you think, yes, moons are always going to be smaller than their parent planets, that means that we're still pushing the limits of what is technically possible to detect.
Could we maybe redefine this discovery as like a dual planet situation?
Well, so there is a definition of a dual planet, what we call a binary planet, which is if you have two objects, one orbiting the other, if their center of gravity, or what we call the barycenter, is outside the body of either of them, then it's a binary planet rather than a planet and a moon. And in fact, Pluto and its moon Charon fit that bill. Pluto, of course, is a dwarf planet, but Pluto and Charon are probably a binary dwarf planet for that reason.
Okay. Interesting, yeah. So there'll be more work to find out exactly what the situation is here, because it's only suspicion at the moment, isn't it?
That's right. There will be more observations to confirm that that the planet itself behaves in a way that is consistent with this large hypothesized moon. We haven't seen it. We haven't seen it yet. In fact, we haven't seen the planet either. But we can deduce things from the way the orbits behave.
Yes, indeed. If you'd like to read about that, the study's been published on the archive, and it has been accepted for publication in Astronomy and Astrophysics. You can also read about it on the dailygalaxy.com website. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Listen, Tranquility Base here. The Eagle has landed.
Space Nuts.
Speaking of big planets with big moons, what about big black holes and the fact that they get big fast? We have always been mystified by this phenomenon. Have they solved it, Fred?
Certainly some work that looks as though it's pointing in the right direction. Yeah, this comes about really, and it's an issue that has only arisen in the era of the James Webb Space Telescope, which has detected the evidence for supermassive black holes very, very early in the universe. Until the Webb came along, we all thought that supermassive black holes evolved over timescales comparable with the age of the universe, that you started off with small black holes, and as time went on, billions of years passing until we get to the universe's current age of 13.8 billion years, that they gradually grew bigger to form the supermassive black holes that we see in today's universe. But when you look further out into space, as the Webb has done, you're looking further back in time. We're now seeing within a few 100 million years of the Big Bang itself, and we find these supermassive black holes already there. And that's the puzzle. That's the conundrum. How did they get so big so rapidly? And they went to McDonald's. That's what they did. The McDonald's of the early universe. Yes, there must be a name for that.
Fast food. That's what it is.
It's fast food. Yeah, I was going to work on drive-through somehow, but that doesn't scan quite the same way as fast food does. It is fast food. That's exactly. In fact, that sums up the research paper by this team of scientists who are actually based in Ireland. It sums up their work very, very succinctly. So the issue is that so what we've got is this set of observations tells us that black holes got supermassive very quickly. And that's a puzzle for the theoretical astronomers who work out how galaxies work, how galaxies form, how black holes form, and all of that great stuff in the early universe. And what has been the point that they've struggled with is that if a black hole starts eating the surrounding material, which is how they grow, the gas and dust that surrounds them, if they start eating that too quickly, in other words, quickly enough to grow into a supermassive black hole very quickly, what happens is the radiation generated by this swirling mass of stuff getting sucked in actually stops the process. It quenches the process of accretion and the black holes growing. That's the way the theory has appeared so far. Mm-hmm. But what the Irish astronomers have done is they've looked at the sort of general turbulence of the gas in the early universe as a background to the feeding black hole. And it turns out that if the universe is a lot more chaotic, turbulent, very violent motions in the background gas, if you've got a black hole in an environment like that, it turns out that they can actually absorb huge amounts of gas, and so they can grow much faster than we originally thought. So one of the authors of this paper, there's a quote here. This is SciTech Daily that is carrying this story, but the research is in one of the research papers. This is one of the authors saying, "We found that the chaotic conditions that existed in the early universe triggered early, smaller black holes to grow into the supermassive black holes we see later, following a feeding frenzy which devoured all the material around them. We revealed using state-of-the-art computer simulations that the first generation of black holes, those born just a few hundred million years after the Big Bang, grew incredibly fast into tens of thousands of times the size of our sun." And another comment, from one of the other team members, "This breakthrough unlocks one of astronomy's big puzzles, that being how black holes born in the early universe are observed by the James Webb Space Telescope, as observed by the James Webb Space Telescope, managed to reach such supermassive sizes so quickly." So maybe that's the answer to the puzzle, Andrew.
Yeah, they ate too much too fast.
That's right, fast food.
And then they get indigestion, and then they have those...
Well, I think that was the problem before, that, they got indigestion, and so they stopped the process.
Yeah.
But what these authors are saying is that if you put them in a really turbulent, field of gas, which we think was in the early universe, then things change. They don't get indigestion; they just go for it.
They just eat it. Don't notice that they're full.
That's right.
And keep eating like a goldfish. Goldfish have that problem. That's why they're so blobby looking. No,
because they don't know when to stop eating.
No, they don't. No, apparently
it's because they can't remember when they started eating. I guess.
Yeah. I don't believe that theory that goldfish only have a 3-minute memory, because I used to keep goldfish and they knew who fed them, because they always reacted when you went near the tank.
Yeah.
The time for food. They're like dogs, except you can't take them for a walk. They tend to die.
Not easily. Got to take their bowl with them as well.
Yes, that's right. Exactly. You put them in a dog bowl, fill it with water. No, let's not go there. But that's a fascinating story, and another one that will probably be subject to future analysis, I imagine.
Yep. That's right.
If you'd like to read about it, as Fred said, it's in scitechdaily.com, or you can read the entire paper start to finish if you're having trouble falling asleep, and that's in Nature Astronomy. Oh, dear. We're just about done. Fred, thank you very much.
Oh, a pleasure, Andrew. Always good to talk, and we'll see you next time.
We will. Professor Fred Watson, astronomer at large. Don't forget to visit us online in the meantime at spacenutspodcast.com or spacenuts.io. You can have a look around. You can visit the shop. You can sign up for the daily news feed. If you hit the supporter page, there are ways to support us if you so desire. We will never make you do it. It's voluntary, and plenty of other things to see and do. And don't forget our social media while you're at it, the Space Nuts Facebook page or the podcast group on Facebook. They're very active, always new members joining there. We're on Instagram as well. And I was going to say something else. Oh, no, I can't remember. Anyway, that's just about it. Also, thanks to Hugh in the studio, who couldn't be with us today. He's gone out the back to brood for not being named Australian of the Year. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.